click on it, see the question, right? Or even after it's due, you might not be able to submit your answer for credit. You can still submit your answer to see if your answer is right or wrong. So try to go over your homework, even if it's overdue. As long as you find the correct answer, have your answer written down. That way, let me know, like you can tell me that I'm ready to update my chapter 1 or chapter 2. So if you have behind homework that's already due, but you still wish to get credit, then make sure you have the answer. So I will reopen it for like a day or two, so you have time to enter your answer. But if you don't have the answer, then keep it for a longer time. It's not that useful. I mean, only when you know the answer, then it's useful to reopen the homework and have you enter your answer. Right. Let me know if you want to make up your test or make up your homework, and let me know. I'll try to either reopen the homework or reschedule the exam. All right. So today we're gonna start. I think I started the recording. Today we're gonna try to start chapter 4. That is really a bivariate distribution. I should look at the resource file myself. Chapter 1 was the overall probability formula, probability rules. Chapter 2 was the discrete distribution, such as binomial distribution, Poisson distribution. Chapter 3 was continuous distribution. Chapter 4, bivariate distribution. That is when you have two variables. And we're gonna have to separate the situation. If you have two discrete variables, how do we look at the relation between the two variables? If we have two continuous distribution, how do we look at it? Now, if we have one discrete distribution, one continuous distribution, what do we do? Normally, we kind of group them together into separate version of the continuous distribution, and that's slightly more complicated. But let's start with 4.1. I actually have two separate files. This is a bivariate distribution, which can involve 4.1, 4.2, 4.3, and 4.4. This one, that was the older one, which is longer. So sometimes I question which one is more useful for your class. But let's start with this one, and if it's more beneficial to move on to a simpler version, we'll try the other version of the material. All right, basically 4.1 was bivariate distribution of discrete type. So the entire chapter 4 was on bivariate distribution. So we have discrete type, we also have continuous type. So I'm gonna start with discrete type. So kind of like with the overall probability, the sequence, chapter 2 was on discrete distribution, chapter 3 was on continuous distribution. Because continuous distribution involves integrations, sometimes we consider that it's slightly harder. Okay. So we're going to try to introduce the bivariate data relation. So if we want to, right, so far what we have considered, what we have practiced, there are one variable. Okay, so there's only one variable, one discrete variable, or one continuous variable. But in actual research, the data set, you with all the trouble to collect data, and then very likely you will ask more than one question. You will collect more than one variable or more than one set of data. So you have more data. So after you get your data, very likely you want to either compare different variable or you want to find the relation between variable. So, right. So in order to understand the relation of variable or pattern behind all the data or variable, we will have to study what's called a bivariate distribution, right? For example, maybe you want to find out relation between temperature and humidity. And maybe you want to find out what is the relation between the high school rank and ACT score. Those people who rank higher tend to have better scores. That kind of question. If you want to answer the question, you'll be looking at bivariate distribution. All right, so we're going to start with the discrete type. So for bivariate distribution, you have to have what people call bivariate discrete probability. And that probability, we're calling it using a two-variable function. So fxy represent the probability that the first variable equal to x, the second variable equal to y. So we end up looking at a multivariable function. Now, if it's discrete, this ends up being a table that has column and rows. So you can study the bivariate distribution of discrete type using a table, or you can use a function. More formally in the textbook, we look at the textbook go by the formula, the function version of the joint probability mass function PMF. It's the name for the bivariate distribution. So our textbooks tend to use a formula for fxy. And when I was solving a problem, because I'm a more visual learner, so I like to have all the number in front of me. So I end up drawing them on the table. Like normally is a 3 by 3 or 2 by 2, depending on how many x value and how many y value, since it's discrete. So it's possible to list all the x value, list all the y value. I tend to put the x value on the vertical margin, the y value on the horizontal top margin. Whatever habit that fits your way of analyzing things. So one of the important things is to figure out what works for you. All right, so some of the rules that the joint probability mass function have to follow, kind of like the discrete probability that we require the function to follow. Number one, because it's a probability, it has to be a number that is between 0 and 1. So probability cannot be negative, probability cannot be higher than 1. So number one is a common property that all probability functions have to follow. Number two, if you're adding up all the probability for all the different situations, the total summation should equal to 1. So the probability x equal to 1, 2, 3, probability y equal to 1, 2, 3. If you add all the different scenarios together, it should be 1. This is a double summation because you have to take a sum over all possible x value and also take a sum of all the possible y value. And so there's a two summation notation here. Last one, if you have a discrete bivariate distribution, the probability calculation will end up being a summation for all the points inside A. So calculate probability of A involving summing up all the x probability for the xy value that's in A. That will be a summation. We are not in the continuous case yet, but to realize that for symmetry, in comparison, in a continuous version, the B will become a double integral of all the density function that you will want. So that's what's going on. For C, in the continuous version, it will be probability of A will be a double integral of the density function. That's the counterpart of the continuous version. But the discrete version, because we are able to add it all together, like one by one, it's normally more direct than the continuous version. Let's finish a couple of examples in the discrete version. So here we have an example. Roll a pair of fair dice, and then you guys suppose the dice has 6 faces each. Then for each of the 36 sample points. So in the sample space, you should have 6 times 6, 36 different scenarios. Now, each one of them have a probability of 1 over 36. All right. So now we're going to name our variable. The variable x is a smaller outcome. The variable y is a larger outcome on the dice. So running the experiment is different than identifying the variable in the question. In this question, we purposely calling the smaller value, smaller outcome as the x and the bigger outcome as a y. So x and y, they're both number between 1 and 6, but x has to be lower than y because every time you toss a 2 die, there's a small one, there's a bigger one. The smaller is always called the x, and the bigger one is called y. Right? So naturally, x is smaller than y, smaller or equal to. So, right. So we are going to try to find out what is the relation between x and y. So when you look at it, you would think about what is the probability x equal to 2, y equal to 3. And then out of the entire scenario, we want to find out how many for that to be happening. So let's try to create a function for this. All right. Right. So when you look at once you identify the variable, and the next thing is create a function. Function's already here. So I'm trying to explain the reason why that works. So like I said, for me, reading the answer from the book is all there is. It's not all there is. You should try to figure out your own way to make sense of it. All right. The top part really is explaining what's going on. So I'm going to erase that part. That was part of the textbook explaining what is x, what's the y. Right. And then the final answer is saying the density, the joint probability function is this. So this is the answer to the question, and then as you can see, the answer to the question is given by a piecewise defined function, but the input value are discrete. The x and y, x does not take on any value, it takes on only the value 1, 2, 3, 4, 5, 6. Y also takes on 1, 2, 3, 4, 5, 6. So this table itself, it is meaningful, but yet it does has some hidden information. That's why I really prefer having the table already. So let's say roll a pair of die. I'm gonna have the table. I don't want to draw it myself because it's time-consuming reading. So here is image for rolling a pair of die. All of these are fine, but number is a little easier than the picture of the die. So here we are. Okay, so let's think about the x value and y value. Because the original identification of them, if we list the x and y, I like to have the x. I'm trying to put them on the table as I mentioned. I prefer having a table rather than the function, but we can then summarize them into the function. So the function goes one step further than the table, but without the table, it's not as visually direct or easy to understand. So x takes on 1, 2, 3, 4, 5, right? And y also takes on 1, 2, 3, 4, 5, 6. 5, 6. So visually, it looks like they could be taking on these values. Maybe I should put on the xy plane. I made it a little different than the textbook. Our textbook went by this way. I didn't want to go against the textbook. So our textbook actually had the y on the vertical axis and x on the horizontal axis. So let's do it this way. This is a x. This is an x, this is a y. This is how the textbook is. So x takes on anywhere from 1, 2, 3, 4, 5, and 6. Y takes on 1, 2, 3, 4, 5, and 6. But we got to remember that x has to be smaller than y. So for example, you have a point 1, 1 if possible, and you could we have 1, 2, 1? That's not right, because x is smaller and y is supposed to be bigger. So this should be one of those. So 1, 2 is fine. Yes, right. So 2, 1 is not, and then anything else. We could have 1, 3. 1, 4, 1, 5, or 1, 6. Any pair that has x smaller than y is fine. Yes. Right, then moving on. So obviously 2, 1 is not okay, but 2, 2 is fine, right? 2, 2 is fine. And then 2, 3, 2, 4, 2, 5, 2, 6. And 3, 3, 1 is not okay. 3, 2 is not okay, but 3, 3 is fine. smaller one and bigger one identical is fine. The smaller one gotta be smaller. That's why it's called a smaller, and called the x. So then we have 3, 4, 5, 6. 4 the same way you have to start with 4, 4, and then 4, 5, and 4, 6, and 5 you start with 5, 5, and that's so visually on the XY plane, your picture of a function. This you can call this the visual presentation of the distribution function, and your distribution function will be discrete, right? A bunch of points. But remember the difference between discrete and continuous. The distribution function for the continuous version should be like a total area of infinite many points, right? Area below the curve. So it's really a different scenario. So right here we have all the sample space. We have all the outcome. This is our sample space. And now we want to find out what is the probability for each scenario. I guess you can attach a probability value to the point. For example, 1, 1. How likely for it to be 1, 1? Out of the entire sample space of 36 of them, there's only one that's 1, 1. 1, 1, right? Anybody attending 1? No. Here's something. I don't know where the sound coming from. Anyway, so then this one has a probability of 1 over 36. There's only one, right? And then how many 2, 2? How many 4, 4, 3, 3, 5, 5? There's only one, right? All the one on the diagonal, they're all 1 over 36 probability. So I'm attaching the probability value to each of the outcome. As you can see, if you write it this way, it's a little bit cumbersome. There's a lot of writing, but here we are. If x equal to y, then the probability is 1 over 36. Now, if x does not equal to y, for example, 1, 2, how many situations when the smaller equal to 1, the bigger one equal to 1? There's 2 situations. That is, one is when we have 1, 2, and the other one is when we have 2, 1, right? 2, 1, 1, 2. If that was what's happening, then the smaller is 1, the bigger is 2, right? So the probability for it would be 1 over 2 over 36. So this is 2 over 36. All right, and that is the same way for all the situations when the x is less than 1. So each one of these, for example, this one is 1, 3. So you have 1, 3, and 3, 1. For this one, that is 1, 6. So you have 1, 6, and 6, 1. That's the smaller one equal to 1, the bigger one equal to 6, right? So whenever the smaller one is absolutely smaller than the bigger ones, you always have 2 over 36. Only for the one on the diagonal, that has a probability of 1 over 36 because it's unique. Right? Among the 36 outcomes, they're equally likely, but here, this is among, how many of them? These are 6, that was a 1. So 7 here, 7 here, so that makes it 14. 14 plus 6, 20. There's 20 outcomes. They're not equally likely, so that's why we have to separate them into 2 different cases. That's where this formula comes from. Any question? Right, so it's one way to analyze it. So we end up having this formula, and this formula is called the probability PMF, probability mass function. That's what we are naming for a discrete case. Okay, so that's the same picture that I was drawing. All right, so the probability that we were writing in the middle, they are called the joint probability mass function. That's what's on the middle. But then we did something else. In this picture, we can add up the entire row, have this probability of 2, 2, 2, 2, 2, and there's 1. So that was 10 plus 1, 11 over 36. 11 over 36 is the probability that the first one, the smaller one, equal to 1. So you add this column, it's 9/36. 9/6 is 36 is probability that is smaller than x equal to 2. So this is a probability x equal to 7, and probability x equal to 3 is 7/36. Probability x equal to 4 is 5/36. And this is a probability x equal to 5 has a probability of 3/36. So adding up the entire column, giving us a probability for x equal to any number between 1 to 6. Adding up the row give us a probability for the y equal to each one of these values. Any question? They do have some symmetry to it. Say y equal to 1 has probably 1/36, but then x equal to 6 is probably 1/36. So these identical value and these two have the same value. Right. So that's kind of, if one is bigger, the other is smaller, x and y. This is, well, the reason I mentioned this is because we gave it a name. The middle is called the joint probability mass function. The one on the margin are called the marginal probability. And this is a marginal probability for x, and this is marginal probability for y. So we can convert a two-variable distribution, such as all these distribution of this probability, into a one-variable distribution. So the marginal distribution actually is a distribution of the variable x, and then this is a distribution of the variable y. So if you want to find what is the probability y equal to 5, right, which is that one, this is when you already have the whole joint distribution figured out. So if we ever want to find out if the x and y is having underlying relations through this, the marginal probability is we have to go through the calculation of it. So let's define it. A marginal probability is suppose x and y has a joint probability mass function. Suppose we already have the formula or have the entire table of probability values, then we can calculate the probability mass function of x alone. So we can convert it to a one variable probability, which is called marginal probability. This calculation is done by summation. So you add up all the possible y value to calculate the probability x equal to x. Okay, that's why we're adding up the entire column. So this calculation of probability 11/36 is a summation of these. It's understandable that any probability calculation related to this discrete case, end up being a summation. And we realize that later in the continuous version, the marginal probability calculation will be an integration over one variable to create a density function of the other variable. So the summation process there is to cancel out one of the variables. Kind of like when you're integrating a variable in the two variable function, your integration of one variable, get rid of one variable, but you still have one other variable. So that's converting a two variable function into a one variable function. So right now the summation action over the x and y variable, add up all the possible y value of the f of x, y, you end up having a function with only variable x. All right, we can also create the marginal probability function for y if we're adding up all f of x, y over all the possible x value. And that is in our earlier picture, that is a summation horizontally. Add up all the x values, we add it all together to get the probability of a single y value, 1.5. Okay, so that's calculation of marginal probability for one of the variable. Any question? All right, so as you can see, the bivariate case, bivariate distribution, we end up having some new name. For example, the probability of x and y, we're calling it joint probability mass function. But the probability we can create using the joint probability is called the marginal probability of a single variable. So these are new name and new terms. All right, since we're talking about relation between two variables, one of the relations is to figure out whether these two variables are independent from each other. Now, based on the probability rule for multiplication rule, the probability of A and B equal to probability of A times probability of B if A and B are independent. So if variable X and Y are independent, we should be able to see this relation that the marginal probability of X times the marginal probability of Y should equal to the joint probability. All right. If that's the case, they're independent. Now, if they're not the case, then they're dependent. Right? So independent, we have this multiplication relation. Now, dependent are not equal. So that's how we confirm independence of the variable. Any question? Okay, so having the joint probability allows us to learn more about how X is related to Y. Are they independent or are they not independent? Now, if they are dependent, they will have what people call correlation. Are they positively correlated or are they negatively correlated? We may have to calculate correlation. In order to calculate correlation, we have to calculate covariance. And there's a lot of other concepts we have to learn. But before that, let's look at how to determine independence with an example. So here we have an example. The joint probability max function of X and Y. So we have a joint probability max function here. F(x, y) equal to x plus y over 21, x equal to 1, 2, 3, y equal to 1, 2. So basically, 2x value, 3x value, 2y value, 3 times 2, 6 the number. So we have 6 probability. All right. With this, the question is x variable independent from y variable? And then we'll try to answer the question from there. What we have in the book, what I'm showing you here is what's in the book. So we will have to, we already have the joint probability. We're going to find the marginal probability. So marginal probability of x equal to summation of all the y value. So we're going to keep x as a variable. Keep the x, and then we're making y a variable. So y takes 1 or 2. Right, so you're going to add x plus y over 21, which is the joint probability. You're going to add the y value, y equal to 1 or y equal to 2. Now, if y equal to 1, x plus 1 over 21. If y equal to 2, x plus 2 over 21. We're adding it, we get 2x plus 3. That is the marginal distribution for x. Now, the marginal distribution for y is you're going to add up all the different x values. X has 3 values. You're going to do x go to 1, 2, 3. X equal to 1, so that's 1 plus y, 2 plus y, 3 plus y. So the numerator ends up having 1 plus 2 plus 6, which is 6. And then there's 3y, and then we have 3y. So that's the marginal probability for y. And then we're going to try to check if these two, this one times that one equal to that one. And they're not equal, obviously, because the variable x times y will be in the formula, but x times y is not in that formula. So anyway, we confirm that they're not independent, they're dependent. All right, so that's what's being presented in the book. We can definitely go more numerical than what's being given in the book. So what we can do is look at the actual number of it, which is the one I prefer. All right, so you can actually make a chart and then try to figure out the relation. I don't know if it helps, but I feel like I want to mention this just so we have a better way to look at things. So we can just very similar to what we had before. We had x here, we have y here. So based on what we already mentioned, there are 3x values. You go 1, 2, and 3. And what we have 2 y values. There's 1 and 2. Now it says here the probability, individual probability is summation of the x times y over 21. So 1 plus 1 is 2, so this is 2 over 21. Now 1, 2, this point will have a probability of 3 over 21. Right, 1, 2, that is 3 over. My writing is really bad. I'm trying to keep it small. Right, over here is 4 over 21. Okay, this is again 4 over 21. Now this is 6 over 21. Well, 5 over 21, right? I was adding a 2 plus 5 is 2 plus 3 is 5. Okay. So numerator goes 3, 4, 5, and denominator goes 2, 3, 4. Okay. So that's what we have here is a joint density. So if you want to figure out the this part is going to be the marginal density. So we're adding this is for the probability x equal to 1. It has a probability of 2 plus 3 is 5. So it's 5 over 21. That is 7 over 21. And that's 9 over 21. So now we're having the marginal probability of x. Adding the horizontal summation 3, 5, 12 over 21. I guess I should use a different color so they don't overlap. 12 over 21 is probability for y equal to 2. And this is 9 over 21. That's the probability for y equal to 1. Any questions so far? Right, then we want to confirm independent. You don't have to, well, this is nice having that total formula. This one times this one does not equal to, it does not equal to this one. You can multiply it and see the numerator and denominator does not equal each other. But to prove non-independent, to prove dependent, you only need one example. So what we can do is we can prove that the probability x equal to 1. Probability x equal to 1 and y equal to 1. It does not equal to the probability x equal to 1 times probability y equal to 1. Probability x equal to 1 times probability y equal to 1. One counterexample is all there is, right? For independence, they were supposed to be equal. Now, if they're not equal, we immediately have that conclusion that we can. So really to challenge an equal equation, you only need one example to show. So this one has a probability of 2 over 21 is on the left. The right side probability x equal to 1 is 5 over 21. And then probably y equal to 1 is 9 over 21. And we can see that 5 times 9 over 21 times 21 does not equal to 2 over 21. And that kind of confirms that not independent. Not independent. For independent, we should have equal relation because they're not equal, they're independent. Any questions? All right, so this is very much a numerical way to confirm that the variable are not independent. This is an algebraic way, which is what the textbook was following. As you can see, a lot of time for the same conclusion, we can use very different approach. All right, another example, which is really the independent case. I'm going to follow the textbook now because there's less writing involved. So we have the original joint density. It says joint probability. That says probability x and y equal to x times y squared over 30. Okay, so if you want to calculate marginal probability for x, you have to add up all the y value. There's only 2 y values. So over here, you guys could go a little bit more into the detail. What did we get the formula from? So how do we get this one? It was given immediately from the text. So this calculation is really the y takes on 102. So you have x times y equal to 1, so x over 30. That's when the y equal to 1. Plus, this is summation, x times y equal to 2, y equal to 2, y squared is 4. So x times 4 over 30. Right. So that will be the case y equal to 1, the case y equal to 2, and you can see x over 30 or 4x over 30. So altogether is 5x over 30. That's why the simplified version of it is x over 6. That's this one, right? This is a joint probability. If you want to find the marginal probability for y, you have to add up all the x values. So this calculation goes x equal to 1. You have y squared over 30. X equal to 2. We have 2y squared over 30. X equal to 3. You have 3y squared over 30. So altogether, we will have 1, 2, 3, add all together 6. So you have 6y squared over 30. Cancel the 6 is y squared over 5. So that's why we get that one. So the summation and simplification. So we end up getting this 2. And then we realize that if you multiply these two together, you get the same thing. So it is true that the x variable, the marginal density for x times the marginal density for y equal to the joint density. So variable x and y are independent. So they didn't affect the overall pattern. The marginal density was able to maintain the same pattern that you see in the original joint density. Any question? This is the example when we do have independent between the variables. So it's really dependent on the original definition or the actual scenario that gave you that definition. So this is another one where they're not independent. In this case, we didn't even summarize, we didn't let x go free between the variables. We are picking out only 3 numbers. So x equal to 1, 1, y x and y, 1, 1, 1, 2, 2, 2, only 3 points. And we give the probability that equal to x times y squared over 13. There's really only 3 probability there. So the marginal probability for x ends up being these 2. I guess, let's see. The question itself is really oversimplified because there's really very little point to work with. But in the meantime, we have to be clear about what exactly are we talking about. All right, so for example, the first one, we're going to calculate what is the probability for marginal probability for x. In this case, the x exam, this is x equal to 1. This is x equal to 2. So for x equal to 1, we're supposed to add up the probability. So which end up being this. So the calculation for probability x equal to 1, you have to have 2 of them. There's probability for 1, 1. You have to add with probability of 1, 2. Right? What is probability 1, 1? 1 and 1. So it's really 1 over 13. Okay, and then for 1, 2, we have that's 1 times 2 squared, 4 over 13. So based on the original density, 4 over 13. After we adding it, we get 5 over 13. That's how we come up with the first number there. The second number really have no problems. There is only one situation, the 2, 2, right? So for that one, x equal to 2, y equal to 2, that's 2 times 2 squared, it's 8 over 13. So where did that come from? There's only one. For the probability of y, right, y can take 2, or y can take 1. So for y equal to 1, it's 1 over 13. For y equal to 2, we have to add the 2 cases. So that will be, there's only 2 cases. If you get the probability y equal to 1, probably y equal to 2 must be the opposite. So you can do the subtraction. Okay, 1 minus 1 over 13, 12 over 13. Or you can just add them. I mean, for the 1, 2, 1, 2, that's 4 over 13. For 2, 2 is 8 over 13. 4 over 13 plus 8 over 13 is 12 over 13. That's where the marginal density comes from. Right, and then you can confirm the independence. For example, for probability of 1, 1 is 1 over 13, but for probability x equal to 1 times y equal to 1, that is different. So probability of 1, 1, it does not equal to the probability of x equal to 1 times the probability of y equal to 1. And you can see it from the calculation. The probability of 1, 1 is calculated using this formula. You get 1 over 13 probably x equal to 1 is 5 over 13. And probably y equal to 1 is 1 over 13. Now we're supposed to multiply them. So that 1 on the right side is 5 over 169. This is 1 over 13. They're very close, but not equal to. So any question? That's another example when the variable are not independent. Okay. We can also use the bivariate graph. It has to be a two-dimensional picture. So graph something in 2 dimensions is a little harder than graph 1 dimension, 3-dimensional picture. 2-dimensional picture was okay. 3-dimensional was difficult. So this we were drawing that one, right? You can see we're using the height of the bar to represent the probability, and then the x value goes from 1 to 3, and the y value goes 1 to 2. Example. All right, so let's talk about expectation. As with this discrete case, mathematical expectation are going to be a summation. Now, since we have 2 variables, it will be a summation of both of these variables. So it's a double summation notation. So if you want to find an expectation of u, x1, x2, you have to take the u value, plug in x1, x2, take the u value, multiply by the probability of x1, x2. It's really how we calculate the mathematical expectation of anything related to xy. Any question? So whenever you calculate expectation of something, the expectation of the variable value itself has to be multiplied by the probability. And let's look at an example. All right, so this question is, there are 8 similar chips in a bowl, 3 marked 0, 0, 2 marked 1, 0, 2 marked 0, 1. And 1 marked 1, 1. A player selects a chip at random and is given the sum of the 2 pointed dollars in dollars. All right, so the higher the number, the better. For example, if this person get the one that marked by 1, 1, they get $2. If they get a chip that marked 0, 0, becomes $0. So if x1, x2 represent those 2 coordinates respectively, their joint probability mass is, right? So this is a situation where it could actually work out. So you have on the chip, you mark out the coordinate 0, 0, 1, 0, or 0, 1, and then you actually put them in the bowl, and then people randomly pick a chip out of the bowl, and the value on the chip affect the scale. Okay, so we're gonna look at how this can be calculated. All right. Again, it's possible to draw a table or a coordinate system to represent these values. Okay, so 0, 0, and then 1, 0, 0, 1, 1, 1. There are 4 values, and then now we will attach 4 probability to it. Then all these numbers, there's 3, 2, 2, 1. What's the total? The total 3 plus 2 plus 2 plus 1. Right? So this is 8, right? So the probability for 0, 0, since there are 3 chips, so the probability in this one is 3 over 8. For this one, if there's 2 of them, so it's 2 over 8, 2 over 8. And this is 1 over 8. Altogether, it equal to 1, right? We okay so far? We're gonna be on the axis because of the 0, so the picture looks a little bit bad. There are different ways to present this. For example, you can make a chart and goes x is 0 and 1. The y can also be 0 and 1. Different representation of it. So however that seems to make sense and easy to grasp. since we're doing expert coordinate system all the time and using the coordinate system right now, so when we have those probability, and you can see that this summary actually makes sense. Trying to explain why we have that. So for example, if x equal to 0, the first one equal to 0, and y equal to 0, that's 0, 0. These are 0, so 3/8. Now, if x equal to 1 and then y equal to 0, 1, 0, that's 3 minus 1, just 2/8. If the other one equal to 1, this one equal to 0, that's still 3 minus 1/8. So all these formula follows. Any question? So it's highly likely to have 0, 0 because that one has more chips. Okay. So now we want to look at the question. The question, now we have a probability. What is the question? The question is, we want to calculate the expected payoff. So on average, how much we get paid playing this game, right? So obviously the probability to be paid $0 is 3/8. The probability to be paid by $1, like here and here, 0, 1, 1, 0, that payment is $1, right? It says here, a player will be paid the sum of the two chips. So the payment will be $1. The probability for it is this two added together. That's 4/8, right? Half of the chance will be paid $1. And then to be paid by $2, that's 1, 1. The probability is 1/8, right? So if you want to find the overall payment, so 0 times 3/8, 1 times, this is together actually, that's $1. For 4/8, and then $2 for 1/8, and the total payment is 3/4. So this calculation is the expected summation of x plus y. That's the payment. Any question? All right. So if there's a positive possible payment, and very likely people are going to charge you to play the game. Okay, because if you play the game, you always get paid lower amount or smaller amount, maybe you get paid 0, but you get paid, it's highly likely you will be paid, therefore you were supposed to pay money to play the game. Okay. This is the example and calculation of the expectation. Any question? Right. So reading through this question, realize this part is given, it's part of the solution. So you might have to figure this one out yourself. Or you can also use this. This is the same thing as here. I think that's a lot easier to manage. And also to me, that's more visual one, easier to grasp. So example. Let's talk about special expectation, such as variance, the moment. All right. I think it was written in a really awful way. I copied over the textbook. All right, we can calculate expectation of either one of the variables. So for example, expectation of x1, we call it mu1. Expectation of x2, we call it mu2. That's why they're xi, mu I. Those are the mean. So mean value for x and mean value for y can be calculated if you do have the joint density. And we go through the same process for the expectation, calculate the expectation. For calculation of the mean for x, you can use marginal probability for x, or you can use a joint density for x, as long as you're clear about the probability. All right, another thing is we can take the variable minus the mean squared. Expectation of this is called the variance. So you can have variance of x1 and variance of x2. So you can calculate variance for both variables, as long as your expectation is calculated correctly. So this is a very much a conceptual definition. Let's look at an example. So we're moving on from the general expectation, we're moving on to special expectation. Mean and variance are a special expectation. But now that we have bivariate case. You should be able to find the mean and variance for both of the two variables in the question. Let's look at this example. Consider a population of 200 students who have just finished a first course in calculus. Of these 200 students, 40 have earned A's, 60 B's, 100 C's, D's, or F's. Okay. So that's 40, 60, and 100. So that's A, B, C's. A sample size of 25 is taken at random without replacement from this population in a way that each possible sample has a probability of 1/200C25 being selected within the sample of 25. Let X be the number of A students, Y is the number of B students. All right, then 25 minus X minus Y are the number of other students. This is so this is a two variable case. So the A is the number of X is the number of A students, Y is the number of B students. Therefore, there are two variables, X and Y, and we're trying to find a probability for X and Y. Okay. This is what people call trinomial. We have there's the total is finite. I guess it's more like a hypergeometric situation. So we're choosing 25 out of 200. That's why the denominator is 200C25. Out of the 200 students, we're choosing 25 students. So the number of scenario of choosing 25 out of 200 is a combination number. So how do we calculate this probability? The probability of X and Y is equal to, or you can just call that F of X and Y is equal to. It's a probability calculation. So we have division. The denominator is 200C25. 200 choose 25. All right. In this 200 students, there are 40 A students, and the number of A student is X. So the 40 choose X. The number of B student is Y, but the B student is 60 students. So this is multiplied by 60 CY. And lastly, all the other student is 100. So we have 100C, 100 choose 25 minus X minus 1. So that's how it is. Any question? It looks like one of the hypergeometric case, right? Except that's two variable. The hypergeometric distribution that we learned in 2.6, 2.5, there's only one variable, and now this is a two variable case. So let's take the two variable version of the hypergeometric distribution. This is what's been given in the textbook. We are using a vertical way to represent the combination numbers. So these are all combination number. It looks slightly different than the one we have. And then we realize if you want to find the marginal density, you will have to add it all together. So the marginal density is when you combine these for all the Y value added all together, it ends up being 40 A students, and the 100 other students, you're going to choose 25 minus X. Then it really becomes the hypergeometric distribution that we have before. So a hypergeometric distribution is a one variable distribution, but then we have two variable case. This is also a non-independent case. Whenever we have selection without replacement, they're often not independent. The variable are not independent because your previous selection affected your following selection. So the X value is dependent on the Y value, and therefore we have a dependent case. Any question? All right. I have one more question. I haven't really assigned it yet, but this discrete. All right, so this is how it looks like in our homework assignment. For some reason, the web work assignment went by not the formula version. So our textbook is actually pretty theoretical. We treated many of the problem using formulas. This fx, y is a formula, and then all these examples we do summarize the probability into formulas. Right, half of x, y, they're simply given by formula, even though we could analyze them into tables. But in our example, we could also create a function for most of the examples having the exact distribution in a table. So you kind of have to get used to both ways. This kind of question actually is, to me, is easier to assign. That's why even if I see a question that was given by formula, I would prefer to write it out into individual table to have it understand. So let's try this question. This question is probability calculation related to the joint probability mass function. So this is a joint probability mass function. Instead of given by a probability x, y equal to a certain formula, now having it spread out and then have them individually listed give us a freedom, because you can actually switch the value for other number. I guess that's kind of the reason what work went by it, because every student have a table like this, and we all have different table. People have identical question. All right. So how do we go about answering this kind of question? We do summation. For all probability question related to discrete case, we often end up adding them all together. For example, the first question is, what is the probability x plus y is higher than 4? So we look for all the cases when the probability of x plus y is bigger than 4. This is bigger than 4. That's bigger than 4. It's bigger than 4. All the other ones are equal or less than 4, right? So the total probability for the first one, the probability is 0.25. Any question? All right, and the second question was, what is probability x times y equal to 4? I don't see any one of them.
There's only one, it's the middle one. We'll be 2, 2.
Oh, right. So yeah, 2 times 2 equal to 4. So the answer will be 0.05. All right, the last one is when x divided by y is bigger than 2. That means the first one is going to be much bigger than the second one. Just 3/1. That's the only one, right? So the answer will be 0.1. Having everything laid out really helps for this kind of question. Any questions? We'll enter 0.25, 0.05, and second question. All right, so we do have conditional probability. We will talk about conditional distribution later in the continuous case. A little bit more complex in the continuous case. But the discrete case, you can pretty much look at the individual distribution. The last part C is very much the same type of question like problem 1, but this one is useful because conditional probability allows us to figure out if they're independent. For example, if probability of A given B equal to probability of A, then they'll be independent. Remember, probability of condition and non-condition, if they're equal, then we have independence. So then part A is leading to part B about independence. So let's try this question before the process done. All right, so let's try to figure out how we answer the conditional probability. So you have to remember what was the conditional probability. It should be calculated. So y equal 1, given that x equal 1. So how do we answer conditional probability? The condition should be in the denominator. Right, and then the numerator should be the joint probability should be like y equal 1 and x equal 1. So that's the numerator. That's how it's supposed to be calculated. So this calculation goes, numerator is 1, 1, and that's this one. So numerator is the 0.15, and denominator, it has to be the total probability for x equal to 1. X equal to 1 is all in, is it all of them? So we kind of have to add it all together, right? So it would be like a marginal probability for x equal to 1. And this is a marginal probability for x equal to 2. You will have to add the entire second row, but we only need the first row. If you add it together, it's 0.3, I think. Okay, so if we divide it, it's going to be 0.5. So we have 0.5. And this one is still the same, but we have y equal to 2. Y equal to 2, x equal to 1 is this one. So it's going to be 0.1 divided by 0.3. That's going to be
1/3.
1/3, yes. So it's 1/3 here. The last one is 0.05 divided by 0.3. It's 1/6. 5 divided by 30, right? This should add it all together equal to 1. Let's see. So now we can answer whether they are independent or not. For example, the first one, if it's independent, it will equal to the probability y equal to 1. So what is the probability y equal to 1? This, the first column, right? This is 1, y equal to 1. So 0.15, 0.05, that's 0.2, so that's 0.3. So the probability y equal to 1 is 0.3. And probability y equal to 1 when the x equal to 1 is 0.5. They're not the same. Therefore, they're not independent. So answer the question. So you're gonna look at this is a no conditional one, and then this is a conditional one. If they are different, then we do not have independence. Right? Remember before? If condition, no condition. If they're the same, then we have independence. So that one. The second question is similar to problem 1, so we'll skip that part. Any question? Let's see if there's anything extra new. So this is a question we have, assuming they're independent, we're creating the joint density. We have marginal density for x, this is marginal density for y. If they're independent, we're supposed to multiply them, right? So for example, y equal to, this is the y equal to 0, 1, 2, 3, x equal to 0, 1. So then for the first block, it should be the probability y equal to 1, x equal to 0. X equal to 0 is this one, y equal to 1. So we were supposed to multiply them too. So out here, it's going to be 0.26. We're creating our joint density. Multiply by 0.4. And over here is x equal to 1, so 0.74 times the 0.4. This y is still 1. All right, so we're going to have 0.26 and 0.26. Because this is all for x equal to 0, we're going to have 0.74 and 0.74 for here. And then we're going to multiply the y. The first is y equal to 1, and then this is y equal to 2. For y equal to 2, we have 0.23. So this is 0.23 multiplied, and we also have 0.23 here. That's y equal to 2. And last one is y equal to 3. For y equal to 3 is 0.37. So we'll multiply 0.37 and then times 0.37. So far, do you have any questions? Okay, so that's the joint density. We apply the fact that they are independent. Because they are independent, we're able to use multiplication to create a distribution table. So you can see that's the actual answer, but I did use a number instead of have the actual answer. Let's finish. Any question? All right, normally we have the joint density, we're creating the marginal density, but if you knew they're independent, you can go from the marginal density, marginal probability to the joint probability. All right, I think this is already given and we're calculating the probability. One of the things is to calculate the expected value. All right, so let's go by an example for the calculation of the expected value. Let's try the x. Right, for example, how do we calculate expected value for x? The first one you can calculate a summation, which is that column. Adding up that column would be it. Now this one we're calculating expected value of x, right? According to the definition, the calculation for discrete expectation is summation x times probability of x. And that is suppose you have the probability distribution of x. Which for now we don't have it. The easiest thing is actually to come up with the probability of x by adding the rows. Are we okay there? Or you can use the individual one. So x equal to 1 times this one, x equal to 1 times this one, x equal to 1 times that one, x equal to 1 times that one, and then x equal to 2 times this, 2 times this, 2 times this. So you can decide not to add it, but you are doing the multiplication individually one that way. But essentially you are adding it anyway, right? You're adding it. So the calculation is going to be 1 time a summation of all these 0.26, that's what it is, plus 2 times, that's 0.4, 0.65. Let's multiply by 0.65. And then plus 3 times, this is 0.09. And that's basically how you calculate the expected value for x. Like I said, you could calculate them one by one. This, and then 2 times this is this, 3 times this is. You can put it in a calculator and do it without writing it up. But this is how I would write it up. Any question? That will be it for today. I think that has already a few examples from the homework. So let's hope that we're doing okay. In the meantime, try to complete all your Thursday homework and bring any questions on Wednesday. I'll see you on Wednesday.